Hello, I'd like to introduce myself. My name's Jen Thompson and I work as a lecturer in mechanical engineering design at Swansea University. And today I'd like to talk to you or introduce some interesting concepts of mechanical engineering by considering mechanical engineering at the movies. So on the slide is a question. What is mechanical engineering? And underneath is a word cloud. So this was generated from answers given by students aged around 15 to 16 when they were asked that question. And how the word cloud works is the larger a word is, the more it's been said in the answer. So there's a couple of obvious ones there. Machinery. So that's something that obviously people tend to associate with engineering. Fixing, so repairing things, building things. Cars seems to have been people's main idea about what mechanical engineering is. And then rather more worryingly, you can see in the left-hand side there is boring. So hopefully after today's lecture, you'll see that mechanical engineering can be described as a lot of things, but boring isn't one of them. And here are some other sort of ideas or images that I found that I think people sort of tend to think about when you mention the word engineering. So people think about measuring things, technical drawings, and yes, that is part of engineering. We all have to learn how to do that when we're engineers. Another thing that people always seem to associate with it is that you will be fixing things or repairing things or getting your hands dirty. And if that's something that you want out of your career in engineering, then you can certainly get involved in that. But there are so many other parts of engineering and mechanical engineering that mean that you might never ever do anything like that. The other thing that people tend to think about then is perhaps sort of dirty, heavy industry. And yes, mechanical engineering is obviously involved in those things. Any process which involves moving parts or machinery or gas and liquids that are flowing, it's all part of mechanical engineering and the design required for it. But it doesn't mean that you actually have to work in places like this. You can just be taking data from processes and then analysing it, and that's all mechanical engineering. And then process lines, manufacturing, all the technologies of manufacturing are sort of underpinned by principles of mechanical engineering, and later in this talk we'll go on to discuss more about concepts of manufacturing. But really, mechanical engineering is probably so much more than you will have ever imagined. It can cover so many different topics, and really when you train as an engineer, you have so many options of where your career can take you and the areas that you want to specialise in. And hopefully from this lecture today, you'll start to see the sort of vast array of options that you would have if you studied mechanical engineering. So in order to introduce some topics and theory around mechanical engineering, I thought it would be quite fun if we looked at different movies and then try to look at them from an engineering perspective. So look at what we see in the movie trailers. I'll be showing you movie trailers, and then try and see how we can pull the science and the engineering out of it. So we'll start off with the Top Gun Maverick, so the new Top Gun film.
30 plus years of service.
So we'll analyze certain images and stills from
Only
it,
man to shoot down 3 enemy planes in the last 40 years.
Yet you can't get a promotion, you won't retire. Despite your best efforts, you refuse to die.
Combat only man to shoot down 3 enemy planes in the last 40 years.
You should be at least a 2-star admiral. Yet here you
Get a
are.
promotion.
You won't retire.
Captain.
Despite your best efforts, you refuse to
What is
die.
Congratulations.
The end is inevitable, Maverick. You kind of headed for extinction.
Maybe so, sir. But not today.
The end is inevitable, Maverick. Your kind is headed for extinction.
Maybe so, sir. But not today.
So in that trailer, there were a few things that really sort of jumped out from an engineering point of view. So this one here was the first thing that I saw in the trailer. And what you're actually seeing here, how this air pattern has been sort of represented to us because it's picked up the sand off the desert floor there, is aircraft wake vortices or an aircraft wake vortex. And these are basically a disturbance in the atmosphere that forms behind an aircraft. And this aircraft wake vortex can comprise of various different sort of flow components, the main ones being wingtip vortices and something called jet wash. So if we consider wingtip vortices, these occur when a wing is generating lift. Okay, so the air from below the wing is drawn around the wingtip into the region above the wing, because there's obviously a lower pressure above the wing, because that's what's causing lift for the aircraft. And because this air is sort of drawn around the tip of the wing, it causes a vortex to trail from each of the wingtips. Okay, so the strength of the wingtip vortice is determined primarily by the weight and the actual speed that the aircraft is traveling at. And wingtip vortices make up the sort of primary and the most dangerous component of these aircraft wake vortexes. And so particularly during takeoff or landing, this region behind the aircraft where you get this turbulence, this aircraft wake vortex forming, can be an issue, because obviously in takeoff and landing the aircraft have a high angle of attack, so that's the angle that the wing makes with the ground or the horizontal. And this sort of, that the greater this angle is, the more issue that you get with these vortices forming. And you can see this is what happened in the trailer here. The aircraft was sort of accelerating upwards from quite a low altitude, so it had quite a steep angle of attack, and these wingtip vortexes and wake turbulence has formed, and we can actually see it because it's picked up the sand off the desert floor. So that's one thing, the first thing. So the next thing then was this image, okay? And what I want you to sort of, you can vaguely see, finely see, you've got a slightly darker region and then a slightly lighter region in the exhaust plume that's coming from this jet engine. Okay, and what we're actually seeing there is due to the afterburner. So an afterburner, so it's jet engine afterburner effect. So the afterburner is a device that's incorporated into the tailpipe of a turbojet engine, and it injects fuel into the hot exhaust gases, which then means that that fuel burns and it gives extra thrust to the aircraft. So that's why we see them on these high-powered fighter aircraft. And then what we're seeing here are shock waves. That's what these darker patches are. So that's another image that I've taken, not from the trailer, but online. You can see very clearly there, these darker sections, okay? And these are basically standing shock waves, we call them. So I'm just going to put another image up now to help us understand a bit better what's happening. So what happens is when this high pressure air comes out of the exhaust and it's been accelerated effectively because of the afterburner, so it's coming out really, really quickly, it's obviously at a much higher pressure than the ambient air that it's exhausting into. And so what happens is we get this really complex and interesting flow phenomena that establishes, and you can sort of see it here in this more sort of scientific drawing. You get an expansion of the gas as it exits the exhaust, and then because it's exiting into this large volume of air that's at a much lower pressure, it starts to get recompressed back, and then we get something happening here, this Mach disk it's called, and basically that's a normal standing shock wave. And a shock wave, we put this other image up here, is called, or can be termed, a discontinuity in the flow. And what that means is you just get something like this, a very rapid, instantaneous increase in the pressure and temperature of the gas. And that's what's happening here. And that's what we're seeing here with these darker regions of flow. And basically all that's happening is you've got a very high energy, high pressure, high temperature gas. It expands out into a much slower moving, low pressure gas, and it's trying to find equilibrium. So the high energy, high speed gas is trying to match in with the bigger volume that it's exhausted into. And so it goes through this complex flow structure, which we show here, in order to sort of match up as soon as it can with the bulk of the air that it's moved into. And that's what we're seeing. Moving on from the afterburner shockwaves that we've just seen, I also saw something else towards the end of the trailer, and that was this image here. So you can see here these three aircraft. If you remember from the trailer, they all came round sort of the corner one after another, and they had these white clouds that sort of appeared in the middle of the aircraft, one after the other, sort of sequentially these clouds appeared. So what are we actually seeing with these clouds? Okay, are we seeing the sonic boom? So hopefully you all know, or you maybe actually have heard a sonic boom with a fighter aircraft. And basically it's when the aircraft breaks the sound barrier. So it starts to travel greater than the speed of sound. The speed of sound is 767 miles per hour. And what we use a term called Mach number. So when something is traveling at the speed of sound, we say that it's sonic and it has a Mach number equal to 1. When something travels greater than the speed of sound, we say that it's supersonic and it has a Mach number greater than 1. And when something is traveling less than the speed of sound, we say that it's subsonic and it has a Mach number less than 1. So are we actually seeing the sonic boom? Is that what these clouds are? Actually, they're not quite, okay? What they are another example of a shockwave. So obviously we've spoken about shockwaves when we considered the afterburner, and they're this discontinuity, aren't they, where the pressure of the gas increases instantaneously in order to find equilibrium, usually. Okay, and what's happening here is these aircraft are obviously traveling very fast, and these vapor cones, they're usually more dramatic or more easily sort of seen when the aircraft is traveling in transonic flight. And what that means is that some of the air flowing around the aircraft is flowing above the speed of sound. Typically the airflow over the wing will be supersonic, but then the rest of the air traveling around the aircraft may not be supersonic, it may be subsonic still. Okay, so that's transonic flight. And so the aircraft itself isn't necessarily traveling faster than the speed of sound, but the air over the wing is. And when that happens, we get these shock waves forming, and then the shock wave obviously is this discontinuity. And what happens is the air can no longer retain the vapor that it's been holding at sort of standard pressure. When the pressure rapidly increases, the vapor in the air condenses out, and that's what we're seeing when we see these vapor cones. Okay, and so typically you see it a lot in imagery taken by the US Navy of their fighter jets, because those jets tend to travel over bodies of water in quite humid, warm conditions. And so that means that there's quite a lot of vapor in the air. And so when the aircraft start to travel approaching the speed of sound, then they tend to have these vapor cones forming. And so you can see there that in the still that was taken from the trailer, those three aircraft are traveling over a body of water. And so that's probably why we can see such distinctive vapor cones forming. So what we're actually seeing is really the point at which the plane might be about to break the sound barrier, and we might hear that sonic boom if they accelerate a little bit further. And this brings about this interesting point of how do we visualize what's happening with flow? So flow is extremely complex. Flow can be laminar, flow can be turbulent. Its behavior affects how things work. So when you're driving in your car on the motorway and you overtake a large lorry, you feel some difference in how the car moves. You can feel how the air changes around it. And these things all affect how we design cars and planes and boats and all these things. But it's very difficult to see. And so this is an interesting image that I found, which is from NASA. And what they've done here is they've actually managed to photograph shock waves of fighter jets in flight. Okay, and they did this in March 2019 because it's taken a really long time to be able to get a technique and all the technology that's needed to get it to work successfully to actually capture these images of shock waves in flight. And the technique that they've used is called Schlerin photography. Okay, so they're actually photographing how the light is refracted because of the shock waves, because when you get these discontinuities in pressure, you're also getting rapid changes in density. And so because the density of the air is different before and after and in a shock wave, it means that it refracts the light differently. And so you can pick up the differences in density, which allows you to visualize the shock wave. And that's what they've done of flights, planes in motion. But I mean, generally, how do we study and design for these flow effects? Because this technique that NASA did is not something that many people would be able to set up and carry out. So how is it that we can understand and capture these flow phenomena as mechanical engineers in order to better understand things and to improve our designs? So obviously, experiments are one approach. Okay, now there's obviously a lot of experimental work that goes into underpinning designs and checking that designs work and improving designs. Okay, but generally experimental work can be very expensive. It takes a lot of time. It can be difficult to set up, and particularly when you're dealing with high-speed flows, it's very difficult to actually measure the flow without affecting it. And what that means is, if you insert a probe in order to measure the pressure or the temperature, then by actually inserting the probe into the path of the flow, you affect how the flow behaves. So, for example, you might actually form a small shock wave in front of the device that you put into high-speed flow, which would then obviously distort or affect the measurements that you were taking. So it's very, very difficult sometimes to actually take accurate experimental measurements of certain types of flow. And certainly it's very difficult to capture measurements of things when they're in operation. So for example, when a fighter jet is in the air flying at supersonic speeds, it's very difficult to get extremely accurate measurements of what's going on. So this is where something called computational fluid dynamics, or CFD, has become heavily utilized by engineers and in mechanical engineering in order to help us understand flow phenomenon, in order to help us improve our designs and better design our systems. So what is computational fluid dynamics? So you can see on the slide there's a very simple volume of fluid. And so when I say fluid, that could be a liquid, but it could also be a gas. In engineering and science, when we use the term fluid, it's basically anything that isn't a solid, okay? So what we do then for computational fluid dynamics is that we take a region of flow and then we discretize it. And what that means is that we break it down into lots of smaller volumes, okay? So we create a mesh on it. And then what we do is we solve equations in every cell of that mesh or grid. So in every little volume, we solve a set of equations, okay, on a computer. And those equations, they're called the Navier-Stokes equations. What they're trying to ensure is that the laws of physics are obeyed effectively, which is that mass, momentum and energy of the flow is conserved. And what that means is what the mass and the energy that the flow has with it moving into the volume that we're considering, it has to equal the mass and the energy that the flow carries out of the volume. It can't just lose mass and energy, it has to move with it. It can change its properties, so it can be at different pressures and different velocities and different densities and temperatures, but it has to all add up to what went in, okay? And that's what those equations are ensuring. And so when we solve them across all the different grids, it means that when the computer model is finished, we can look at the results and then we can see exactly what the flow is doing. So we can visualize the pressure and we can visualize the velocity and temperature and a whole other range of different quantities. And we can add in different equations which allow us to solve for different things like chemical reactions or heat transfer. And then we can visualize all those different effects as well. And so are some images that were taken. If you just Google computational fluid dynamics, you'll see millions and millions of images of different models that have been run. And these were just some that I selected. And you can see, you can visualize the flow. So the top left image of that truck, you can see that you've got flow that's recirculating or going in a circle. You've got this turbulent effect behind the cabin. So as an engineer, you could design the shape of that cabin to change that. Maybe you want more, maybe you want less, maybe you want to change the direction of it. And then obviously the other thing that we can clearly see in the image there is that somebody has done CFD of the afterburner exhaust is on a fighter jet. That's image in the center. So we can actually visualize and see and approximate what the pressures and the temperatures are of that exhaust plume. Well, that would be impossible to measure in flight, but if we apply the correct conditions and setup to our computational model, it means that we can approximate that and we can then better design our aircraft. So computational fluid dynamics and mechanical engineering at Swansea University. So as part of your undergraduate mechanical engineering degree, you will study modules on thermodynamics, fluid mechanics, and computer-aided design, okay? And these will form the building blocks of CFD. So you cover the sort of the initial theory around the fluid, which will help you then to go on later on in your career if you want to use CFD. We also have the Zinkovich Centre for Computational Engineering, and this has been at the forefront of international research in the area of computational engineering for over 30 years. It pioneered the development of something called the finite element method, and there's Professor Zinkovich, and that was sort of one of the tools then that was used to help solve these computer codes for CFD and similar topics. And we also have a state-of-the-art wind tunnel for experimental aerodynamics, so we can actually do some experimental work to help validate or confirm that our computational models are correct. And you can see there's an image of the Bloodhound SSC, so the supersonic car, and a lot of the initial CFD work for the design was undertaken at Swansea University, running different CFD models and developing code in order to approximate what the airflow would do around the car. So now we're going to go and we're going to look at another movie trailer, and it's going to take us on to a completely different topic of mechanical engineering.
We designed them to be trusted with our homes. We designed them to be trusted with our homes. With our way of life. But did we design them to be trusted?
The rollout of USR's new generation of robot, the NS5, was barred by the death of designer Alfred Lanning. The NS5 was barred by the death of designer Alfred Lanning.
Bird is a new trick for a robot. Respond. Bird is a new trick for a robot. Respond.
I miss the good old days.
One good old days.
When people were killed by other people.
The good old days.
My robots don't kill people.
That thing threw somebody out of a window. Is that registering with you?
Don't kill people.
That thing threw somebody out of a window. Is that registering with you?
A robot cannot harm a human being.
The loss of all that we gain because of the rash for protection. Imagine.
Does thinking you're the last sane man on the face of the earth make you crazy? Because if it does, maybe I am. Thinking you're the last sane man on the face of the earth make you crazy? Because if it does, maybe I am.
Maybe you can be looking in the shadows all the time.
You're on the inside. Help me find out what is wrong with these robots.
Dr. Lanning suggested robots might naturally evolve.
I was hoping to see you
Dr.
again,
Lanning
Detective. Think
suggested
of me as your
robots might
friend.
naturally evolve.
Why don't you just hand the world over on a silver platter?
Maybe we do. We are on the eve of the largest robotic distribution in history. There will be one robot to every 5 humans.
How many robots have ever committed a crime?
There will be one robot to every 5 humans.
How many robots have ever committed a crime?
There is no conspiracy. What this is one mistake. There is no conspiracy. What this is one mistake.
Oh, hell no.
Somehow, I told you so just doesn't quite say it. Somehow, I told you so just doesn't quite say it.
You know what they say about old dogs?
Not really.
Gotcha. You know what they say about old dogs?
Not really.
Gotcha.
So why did we look at that clip? I'm not trying to say to you that there's going to be an uprising of robots that are going to take over the world. I want to try and introduce this concept of Industry 4.0 to you. Okay, and so yes, robots are going to be a part of Industry 4.0, but they're only going to be a small part. Okay, it's going to be the coming together of lots of different technologies that have been developed and are in the process of being developed, and they're going to come together to revolutionize our manufacturing industry, and then consequently that will have a huge knock-on effect on how society and how we function as a society. So first of all, if we look back over the industrial revolutions, so before there was any industrial revolution, we were in something called the craft production stage. And what that meant was people didn't really travel. They lived where they were born, in the towns and villages where they were born. And things were made, they were bespoke. And, you know, it was things like carving and knitting and sewing. And people tended to make their own things as well. And if you did buy something, it was very rarely because it was so expensive. Okay. Then what happened around about 1784 was we had the start of the first industrial revolution. And what happened was that there was a sort of the coming together again of technologies that had been developed, and the main one was steam energy. So because people had figured out how to harness power from steam, from burning coal, they were then able to mechanize things. People then also designed mechanical looms, so things to make fabric. And these things came together then where we had these steam-powered mechanized looms, which meant that all of a sudden you could produce a lot of fabric. And then the mills started up in the north of England. And so all of a sudden we had factories and we had this increase in production of things. We also had iron, so metallurgy techniques were improved. So iron could be made, so things like train tracks could be made. This combined then with the fact that we had steam-powered trains meant that we had a transport network. And so it was the coming together of several technologies which allowed us then to take this big step forward, and this was the first industrial revolution. Then sort of around about 1870, things started to move on again. And again, the second industrial revolution is brought about by the coming together of several developments in technologies. So this time you had electricity, which meant that the light bulb was invented. We also had an improvement in communication systems because the telephone and telegraph was invented, which meant that people in different countries could talk to each other, which meant that trade became globalized. We also had greater improvements again in our metalworking techniques, which meant that we could produce steel, which meant that it was easier to build railway lines and things. And so again, you just expanded the whole manufacturing process. The other thing that happened as well for the first time was this concept of mass production. And this was obviously Henry Ford, so of the Ford Car Company. He made something called the Model T car. And how he did it was that every car was identical, same colour, same parts in it. And because everything was identical, it meant that a system could be set up, the process line, which was very effective in making cars quickly, which meant the more cars that could be made, they could be sold more cheaply because more could be sold. And so you had this idea of mass production. Then around about sort of the 1950s, we moved into the third industrial revolution. And this was all about computers, microprocessors. It was about sort of bringing a level of automation into the manufacturing line. And it was also about trying to optimize, so improve things. So concepts were brought in to make manufacturing more efficient and to use resources more efficiently. And that's kind of where we've moved through now, the third industrial revolution. And we are on the brink, or already sort of moved into this fourth industrial revolution. And again, it's all about the coming together of multiple different technologies that when they're brought together, they're going to advance us in our manufacturing centre, and consequently, they're going to advance us as a society. So Industry 4.0 can be thought of as all these different technologies that are going to come together to help move us into this fourth industrial revolution. Okay, so certainly it's going to be the future of manufacturing. And what it's looking to do is to take the more physical, so the real world, the real manufacturing processes, the actual product as it functions, and the virtual world, so data about that product or simulations like CFD of the design of that product, and sort of bridge the gap between them so that they work together in a loop. And by having this, it's going to make everything much more efficient, and it's going to improve understanding and optimization of how we do things and how we use our resources. So it's really going to change not just the manufacturing sector, but our society as a whole. So I'm going to introduce some of the key concepts of Industry 4.0, or the technologies that are going to come together effectively to push us into this fourth industrial revolution. So big data is probably the backbone of Industry 4.0. It's this idea that we're all going to, all processes and products, they're going to be acquiring data, and that data is going to be stored and used. And so part of that is that we're going to be having things like machine learning algorithms. So these are computer codes that can take data and identify patterns and show us how to be more efficient, or potentially highlight things that could be a problem. And so the more data that we have about things, situations, products, the patterns of people's lives, then we can understand things more by using the data with these algorithms. And also, probably another term that you might have heard of is artificial intelligence. And these are forms of machine learning algorithms. And sometimes people are a bit frightened, like with the iRobot trailer, this idea that the robots are going to come and they're going to sort of overthrow us and overrun us. You know, it's this same idea with artificial intelligence that, you know, we're handing autonomy to a computer code, but it isn't really like that. It's about utilizing them to better understand data. And you've probably all actually had interaction with AI in some way. For example, things like Netflix. When you're watching your programs, they are acquiring that data about you. They're understanding what programs you like to watch, what topics are interesting to you. And so you can see then when a new program comes up on the list, it gives you a percentage match. And that is artificial intelligence effectively. It's looking at your preferences based on historically what you've watched, and then it's comparing parts of that program or the keywords to do with that program with this new program, and then it's matching it to you, and it says, yes, that's something you probably like. And that's artificial intelligence. So it's nothing to be afraid of. Another technology then is additive layer manufacturing, or 3D printing. And so this very much comes into this idea. I'm going to introduce another term now called mass customization. Okay, so this is one of the big drivers as well for Industry 4.0. So remember when we said in the second industrial revolution we had mass production, and that was this idea of producing lots and lots of the same thing. They were identical, but because we had this economy of scale, it meant that we were producing things more cheaply because we were producing so many of them efficiently. Well, this idea of mass customization is actually more about having bespoke products. So because we've got this data now about a person, about how they use a product, because we've got data about how a product is used and how we can best manufacture it, and now we've got this technology like additive layer manufacturing, which means that we can quite efficiently print and produce bespoke, unique designs, and we don't have to set up a manufacturing line to help us produce a completely different part. All we have to do is put the design into the ALM machine and it will print it as it is for us. So that means that we've got this capacity now to actually produce bespoke one-off products for people. Okay, and this is mass customization. The other thing then, which is very much in line with the iRobot trailer, which is why I chose it, is this concept that robotics are going to become more of a function of the manufacturing process line and possibly of our day-to-day lives. The interesting thing about robots is the actual term, so the word robot, came from literature first. It was in a play, in a 1920s play by a Czech writer, and he introduced this concept of having robota or robots, which were sort of forced labour workers. So it's funny that actually the literature and the idea came before the technology that was able to create them. But what we're going to do in the future is we're going to move away from robots as these systems that work separately from humans. You can see in the image there, you've got those orange robotic arms which are obviously working on a car manufacturing line. But you can see either side of them, there's that grey fencing, okay? And that's because typically in manufacturing process lines at the moment, robots are kept completely separate from the human workers. And that's because obviously robots are extremely big, heavy pieces of equipment. And if there is any sort of malfunction in them, then they can obviously cause quite a lot of damage. But Industry 4.0 is going to see us move more towards this idea of collaborative robots or cobots. And these robots will actually be designed in such a way they'll be lighter, they won't be as heavy, and they'll be less likely to be able to damage humans. And so they'll actually work alongside humans. They won't take over all human tasks. There'll be certain tasks that they'll be suited to, usually the more mundane or dangerous tasks or, hazardous tasks, but they'll be able to function alongside humans. And potentially we may come to a stage where we do have some sort of cobot helper within the house, certainly to help perhaps with people that have got health problems or live on their own. They could be sort of like a health assistant. So these are ideas that are sort of moving forward with Industry 4.0. And then the final technology is this idea of virtual reality and augmented reality. We're obviously all familiar with this idea of VR and putting the headsets on, and perhaps people associate them more at the moment with computer gaming. But actually they're going to become more of the sort of standard part of the workforce. Okay, you're going to help us visualize things, going to help us interact with people. And so it's all going to come together, all these different technologies. It's these merging together that are going to help us move into our fourth industrial revolution. Just concept for that then. And this is the Internet of Things. And I just want to introduce this because if we've got all this data and we've got this connection between the physical world and the virtual world, we need this way of communicating the data and between those, and this is the Internet of Things. Okay, and so we are starting down that path. If you think about smart meters in our homes, they take data about our energy usage and they provide that to the energy grid. And what that means is that the energy suppliers can have a better idea of the quantity of energy that's used, how different households use energy, what different times of day, and it means that they can better optimize and equip the energy supply system. So that's sort of it creeping into our day-to-day life. But in order for all the data to be transferred and stored, we're going to have to implement this idea of the Internet of Things. So Industry 4.0 and Mechanical Engineering at Swansea University, you do actually have an undergraduate module on Industry 4.0 at the university. And there we go into a lot more detail about big data. We look at different machine learning algorithms. We consider the different technologies. And we also think about different aspects like cybersecurity and how we can implement protocols and methods to make sure that when these technologies are brought into companies, it's done in a sensible, structured way. We'll be preparing you to work as engineers in the fourth industrial revolution. So we have 3D printing labs at the university. We've got a new research institution which has just been built and opened, which is specialising in materials processing and numerical technologies, so this big data side of things. And looking down the line, there's going to be the development of the Factory of the Future, which is actually looking to develop and demonstrate a lot of the Industry 4.0 technologies in partnership with industry. So we'll have one final trip to the movies, and this topic will take us back on to more of the sort of traditional topics and ideas that we associate with mechanical engineering.
That's what separates them from mere mortals.
All I ever do is pray for a safe race. All I ever do is pray for a safe race. One day watching my son. I never thought that I'd be there one day watching my son.
For me, it's heart attack after heart attack. For me, it's heart attack after heart attack. Are you okay, Nico?
Get me out, there's fire. There's fire.
I love the danger, that adrenaline, that excitement. I love the danger, that adrenaline, that excitement.
They have crashed! They've gone into each other!
To get the best results possible. I'm not worried about dying. To get the best results possible. I'm not worried about dying.
So Formula One is obviously something that springs to mind as very much a mechanical engineering topic because it's cars, it's engines, suspensions. But Formula One is really to be admired within engineering. They are very much at the cutting edge of developing all sorts of technologies. Obviously their focus is to develop the technology for application in the Formula One car, but because of the ingenuity and the ideas that they come up with, a lot of those can then be taken and actually applied to very different scenarios in life and have enormous benefit. So I've got a few examples down here on the slide. So the baby pod incubator. So this was actually based on the carbon fiber developments that they came up with to raise the standards for the Formula One drivers' safety cells. So you can obviously see in the image on the right, there's a crash, and how the sort of Formula One cars have been developed is obviously there's parts of them that literally disintegrate at a high impact crash, because obviously that dissipates the momentum of the crash and the impact, which obviously means that the driver in this carbon pod that they've created is more likely to be left undamaged, which is obviously their focus. But that was taken and then used as a lightweight system to attach to a transport stretcher, and then they used it in intensive care ambulances run by Great Ormond Street to transport these very premature and very ill babies. So that's not necessarily something that you would automatically associate with Formula One, but you can see that that technology has been taken and applied for a very good cause. Then there's aerofoil technology, and this was taken from the front wing. So obviously the front wings on the Formula One cars are all about creating downforce, so keeping the Formula One car on the tarmac at high speeds. But they could take that design, and what they've actually done is attached it to supermarket fridge shelves to channel the cold air from spilling out into the aisles. So obviously keeping more of that cold air in the fridges where the supermarkets want it. And this has resulted in significant energy savings. So when they sort of did a study of the potential savings in energy, what they found was that it was the equivalent of a month's worth of the domestic carbon dioxide emissions from a city the size of Manchester was saved by attaching these front wing designs to the supermarket fridges. CFD, which was developed for Formula One, a certain approach, created a sensor-based air particle detection system designed to protect soldiers from incoming biological attacks. So that's not something that would have sprung to mind when you think about Formula One. The telemetry that's used in racing, so that's where they sort of have all these sensors on different parts of the car, the engine, the brakes, everything, and how they're timing everything, all the laps, all the different functions of the car. They have these extremely complicated telemetry systems. Well, they're taking that technology that they use in the racing, and then they're actually applying it to the monitoring of people's health in health studies. And so that very much sits within this idea of Industry 4.0 that we were talking about, where if you've got the ability to monitor and track people's health, and you've got this ability to process and analyze data, then it means that you could potentially predict and prevent somebody from having a heart attack if there were certain indicators that your monitoring was picking up. So these are all the ideas that Industry 4.0 will help us manifest as well. They've also been using virtual design systems, so this idea of having AR and VR in the design process, so you can see Formula One are really ahead of the game. They're already in this Industry 4.0 approach. And they've also come up with the idea of flywheel energy storage technology for fuel reduction. So that's obviously thinking about the impact that we have on the planet and the resources that we use. So obviously from that list, you can see how, yes, Formula One's focus is about car design, but those design approaches and ideas can then be taken and applied to all different walks of life, which benefit society in all different sorts of ways. And that really is what engineering is about. So considering Swansea University, we have the Formula Student programme. So we have Swansea University Race Engineering, or SUA, and this group, they design, build and race cars for the Formula Student competition. So Formula Student is when these Formula Student teams from universities all over the world will design a Formula race car, and then they'll come and they'll compete at different sort of categories and at various locations. It can be anywhere in the world, changes from year to year. And so the actual SUA team within Swansea is made up of students across all the different engineering disciplines and from all the different years, and postgraduate as well. And the topics that you cover studying mechanical engineering at Swansea are obviously extremely relevant then to how you would design and develop the car. So that's really, if you're interested in that side of things, maybe a career in Formula One or the automotive industry, you can then do that, and that sort of filters into your studies. So thank you for listening to this lecture today and watching it. Obviously come along to a virtual, obviously at the moment because of the COVID-19 situation, open day. Find out more about us, find out more about the department. It would be great if you did come to study mechanical engineering with us at Swansea University. And I think with that degree, you would very much prepare yourself to have a diverse, challenging and fun career. And we've got state-of-the-art facilities at Swansea. So yeah, come along and find out more. Thank you.